So let's start with four-stroke internal combustion engine. So under that heading, we are going to talk about like petrol engine, and other is the diesel engine. So let's start with the petrol engine. So you see here, this represents this represents the system. So this is basically let's say this is the cylinder. Okay, so this is the cylinder, and this piston can move up and down because of the help of there is rotating the crankshaft. So the piston is basically this piston. You see this piston rod. This piston is joint is connected to the this shaft, and it could move the piston up and down. Okay, so start with that picture. In this case, this is called the intake stock. So in this case, air is mixed with the fuel during the intake stock. So this means this valve is open, and the other valve, this valve is at that time this is closed. Okay, so the gas means in that time air is mixed with fuel that will enter through this valve. Okay, so you see that after that, what will happen during the compression stroke? During the compression stroke, the fuel, the air fuel mixture is rapidly compressed. Okay, but this happened in this adiabatic fashion. Okay, and the piston raised with the volume with the both valve closed. So at that time, what will happen? This valve and that valve both is closed. This valve is also closed. This valve is also closed. Okay, and the this gas inside the cylinder will get closed, compressed. So you know that volume is going to decrease. So it's called the work is done on the gas because volume is decreasing. Okay, so this is the second part, second page of the engine. Next, this is the actual motion. This is the actual role that the piston plays here. This is called the power stroke. So power stroke has two distinctive parts. The first, the air fuel get ignited. Okay, so because of this is a get is because of a spark, it gets get the ignited, and it converts chemical potential energy into the heat energy. Okay, almost instantly, and which lead to a great increase in pressure as piston going down. In that situation, volume will increase. So the gas, in this case, the gas does the work. Okay, and in the final stage, the exhaust stroke expel the hot gas to prepare the engine for the another cycle and start again the intake stroke. So this means this cycle will be repeated again and again. Okay, so this motion means intake stroke, compression stroke, power stroke, and the exhaust stroke. Can This all goes through a complete cycle, and this can be represented by this diagram. It's called the PV diagram. In this scenario, this is also called the Otto cycle. Okay, the Otto cycle in this scenario. So you see that initially, let's start with this picture. Okay, in the first A, fuel enters. Fuel means we're talking about air and the gas of the petrol enters at this point. So you say initially its pressure was the atmospheric pressure. So we start from O point. So at that time, say this pressure is P naught. So this pressure P naught is say this is the atmospheric pressure. Atmospheric pressure. at that time, the volume of the gas initially is corresponding to that. At this location, volume is 0. Okay, so means the in this stock, what will happen is that at constant pressure, volume will increase. Okay, so this is called the intake stock. Intake stock. So this means at that stock, what will happen is that volume will increase. So volume will increase. So at that point, we can say the volume is VA. Okay, volume is the VA, and the pressure is the atmospheric pressure. Okay, so we can represent by symbol. Say we can say at that time pressure is PA, volume is VA, and we can say temperature is TA, kind of thing. Okay, then let's start the other stock. Okay, other in this. Then after that, what will happen? There's a adiabatic compression happens. Means in this case, the temperature of mixture increase raises as the piston compresses adiabatically from volume VA to volume VB. Means now the gas get compressed, clear from here. So at that location, we can say pressure is PV, volume is VV, and temperature is TB. Okay. So then we go to the ignition at constant volume. Okay, so if that's time, you see here it will happen at constant volume. Okay, at constant volume. So, okay, so this means at that time it will go from B to C. So at point C, pressure will be PC, volume will be BC, and temperature will be TC. Okay, again the cycle will be repeated. Again, what will happen? There is a adiabatic stroke will happen. So at that time, what will happen? The heated mixture of gas expands. Okay, so in this case, it go from C to D, So pressure will be PD, temperature volume will be VD, and the temperature will be TT. Okay, this is this one AB and BACD is the process is called the adiabatic process. A to B is the adiabatic compression, and C to D is the adiabatic expansion. Okay, so finally you see D to A is called the constant volume volume kind of adjust. At that time it happens at constant volume. So again it go from D state to D state. So at that time it is going to release heat to the atmosphere or the sink. Okay, finally it's called the isobaric compression state. Means it will go from A to O. Okay, A2O means what will happen? Its pressure will at constant pressure is volume. Finally again it becomes initial state. So our initial volume, what is starting with 0, it repeats. Again finally it goes to the 0. So this process is repeated again and again. So the final point is that this area under the curve, this represents the total work done. Okay, this means from B to C, heat enters the system, and from D to A, heat will go to the sink. So the here B to C, when it goes to the B to C, what will happen? Heat QH enters the system. Okay, And from a D to A, what will happen is that heat QH, QC rejected to the sink, rejected to the sink. Okay, so this means, this tells you that total work done, W will be the QH minus QC. So this means this some part of the supplied heat is converted into the work. Okay, so this is the complete meaning, complete steps how this kind of petrol engine will work, and this cycle will be repeated again and again. Okay, let's do some math. So here we want to prove our goal. I want to prove is this, to prove E value is the efficiency of the engine. Okay, we want to prove E equals W over QH, where QH is the heat supplied. This must be equal to QH minus QC over QH. So our goal is to prove that E equals 1 minus 1 over R, and it's the gamma minus 1. Okay, so here gamma is the ratio of a specific heat capacity, ratio of a specific heat capacity. Okay, so this is basically Cp over Cv, and this R will come to this point is called the compression ratio. Compression ratio. So our goal is to prove this. Okay, so let's start how we do this math. So let's start that QH is the heat supplied to the engine. So let's check the picture. This happens from it happens in the step B to C. So it happens at constant, keeping the volume constant. Okay, so QH can be written as N CV dt. Okay, so N is the number of mole of gas inside the system in the cylinder. Okay, Cv, is the specific heat capacity, is the specific heat capacity at constant volume. Okay, volume, and dt is the here is the change in temperature, Okay, so this is this happens for B to C in the picture. Okay, so from the picture you see that we can write N Cp, change in temperature will be temperature at point C minus temperature at point B. Okay, so this is the QH. We know this point. Let's make the let's specify the temperature, pressure, volume of each. So point A, state A corresponds to pressure PA, volume BA, temperature TA. Point B corresponds to pressure PV, volume PV, temperature TB. Point C corresponds to pressure PC, volume BC, and temperature TC. And point D corresponds to pressure PD, volume PD, and temperature TD. Okay, so if you consider the point B and C, for B and C, this is same. For the B and C, it will be before the B and C, you will see that volume, this volume will be the same. So VB equals VC. Okay. So similarly, we can see for part, our goal is to find QH over QC. So we need to find QC. QC, if you see in the picture, in the graph, PV diagram, heat will be rejected from in the region in the region D to A. Okay, in due to for this region, we can write for D to A. We see that this QC is the heat actually rejected, okay, to the sink will be N CV dt. So this is the heat rejected to the sink. This is not the heat at point C, okay? And similarly, this is the QS is the heat entered, instead of entered, we can say that heat to the system. Okay, it's supplied to the system in simple word. Okay, it supplied to the system. Okay, so we can write this similarly as N CV. In this time, temperature is TA minus, you can write temperature TA, just I'm writing the symbol, TA minus TD. Okay, now we can plug those values. We have QC and QA, so I'm going to plug under there, so our value will be, yeah, efficiency E will be efficiency will be QH minus QC over QH minus QC over QH. Okay, just plug those values, so we get the value N CV TC minus TB, okay, TB plus N CV TA minus TD over NCV TC minus TB. Okay, so we can write this way. So be careful that this plus symbol here, this symbol, because of this region. Okay, so it means this equation can also be written as QH mode, means positive value plus in that scenario, we can write this as so this is basically same thing as this. We are taking the positive value QC, okay, QC over QH. Okay, so if we consider these situations, this gives you this situation. Okay, so let's go, let's solve further. So if you consider this part, we can simplify like this. We can cut N, CV, they cancel out from both. Okay, so we are left with TC, we are left with E equals TC minus TB plus TA minus TD over T C minus T B. Okay, so our goal is to simplify this further. Let's see. Then we can use our relation TB gamma minus 1 is equal to constant. Okay, this we can use this for AB. Okay, because AB is the adiabatic process. Okay, similarly we can use them same equation for CD. Okay, because this is also adiabatic. Okay, so this is also the adiabatic process. Okay. Let's do that. What will happen for this AB part? We can do T A B A gamma minus 1 equals to TB B gamma minus 1. Okay, so say we assume, say we have, say PA equals R. Okay, BA equals R, R equals say this PB. Okay, we are just assuming. So R is the ratio. This is called the compression ratio. This is the compression ratio. Okay, so means if VB equals to V, that will give you PA equals to gamma V. Okay, so we are using this thing over here. So if you do that, you will find that is TA gamma V R RB. Let me write again. So this is I'm removing this part. Okay, so this is R, this is R, this is also R, so this is gamma minus 1. This must be equals to TB P gamma minus 1. So I can further simplify as TAR gamma minus 1 must be equals to TB. Okay, TB. So I got this result. Similarly, I can do same thing for the part CD. So it will be TC BC gamma minus 1 must be equals to TD PD gamma minus 1. Again, as before, I can write TC. This is VC is basically B gamma minus 1 must be equals to TD. So it is R B gamma minus 1. Okay, so but if you further simplify, it will gives you TC equals TD R gamma minus 1. So I will be plugging the value of these into that equation. Okay, so if I use these results, this and that result, and put over here, then we get some simplified. Okay, so for some kind of simplifications. So let's simplify further. So E equals, we are putting just the number, we are putting this value, so it will be d r gamma minus 1 minus ta minus ta minus tar gamma minus 1 plus ta minus td over td r gamma minus 1 minus ta r gamma minus 1. Okay, so let's rearrange again. So we can write r gamma minus 1 equals times td minus ta. So we combine these two parts. Okay, so plus ta minus td over r gamma minus 1 td minus ta. Okay, so we can cancel these, this one, that one, and that one. If you do that, we'll find it will be r gamma minus 1, certainly this will be minus, equals r gamma minus 1. This will gives you 1 minus 1 over r gamma minus 1. This is the efficiency. Okay, so in this way we can find the efficiency. So r is called the compression ratio, as I told before. This is the compression ratio, and this gamma is the ratio of a specific heat capacity. It will be basically Cp and Cp of the gas. Okay, if you have understand that point, you can solve this problem. Okay, so if the R value is 6 and Cp over Cp is 1.4, you can find what is the theoretical efficiency of the engine using that equation is 0.51. Okay, next go to the a diesel engine. This also is a internal combustion engine, and it also goes through the same cycle. But you look at here, the PV diagram is slightly different. In what sense they are different? Initial volume started from here. Here you see volume starting at that time is equal to 0, and this pressure is the atmospheric pressure. Okay, this is the atmospheric pressure. Okay, so let's see, means at that time it goes to so only air is drawn into the chamber during the intake stroke OA. Then air is then compressed adiabatically from state A to B. Okay, A to B. So this process A to B is adiabatic. Okay. So in adiabatic, dq is 0. Now here is the main difference between petrol engine and this engine. This is the diesel engine. You see, instead of going constant volume, we are going to the pressure constant. So this region B to C is the constant pressure. Means the gas gets heated, the gas will get the energy at constant pressure. Now C to D is again, this region is the adiabatic. In the adiabatic region, there is no heat gain or heat loss. Okay, so you see here that so it says that raising the temperature high enough so that when fuel is added during the power stroke BC, it ignites. After ignition ends at C, what will happen? There is a further adiabatic power stroke, CD. So CD is also the adiabatic process. Then in this section, DA, the engine will lose the heat Q2 to the sink. So this is this Q2 heat, this heat goes to the sink. Okay, this is the heat gained by engine. Okay, so in this process, you see that finally there is an exhaust at constant volume as the pressure drops from PD to PA. So pressure is not constant in this cycle. Volume is constant. So pressure at constant volume, pressure will drop from this point D to A. Okay, but volume is constant. So finally at A, it again comes back to its original state where the volume is zero, means the the cylinder is empty. Okay, so this cycle is repeated again. So as done before, you can do exactly same math and you can prove this. So you can prove this doing exactly as before, doing same, or we can say similar step as for petrol engine. Once you get that equation, use this concept to get this point. You have to use the concept of A and B. Means you have to use how to find the work. Means you have to find Q1 and Q2. So in this case, Q1 and Q2 represents this situation. So so it's equivalent to, you can use Q1 is basically the equivalent to QH, and Q2 is same as, only the symbol is different, so it is QC. Okay, so if you do the exact same math, you will get this equation, and once you plug the informations given here, okay, given informations over here, then you can prove that the value of efficiency is this. Okay, so you are doing exactly same math to get this equation.